The coronavirus is the family that SARS is a part of. So SARS stands for Severe Acute Respiratory Syndrome. And in 2002 and 2003, there was an outbreak of a novel virus in China, in the Guangdong province. And it started out as a severe atypical pneumonia that was diagnosed basically as not having any known other viral component. Usually coronaviruses just give you a cold. What was unusual about SARS is that it was so lethal. And none of the other coronaviruses in humans actually cause such a lethal disease. And during the epidemic, there was around 8,000 people infected, around 800 people dead, so around 10% died from the acute infection from the virus. There was a novel coronavirus that was first reported in September of 2012. It's now called human coronavirus EMC. And what we know is that EMC at the sequence level, it looks like two other known bat viruses that are bat coronaviruses. The parent virus, and the reason that's interesting is that the parent virus of SARS came from bats. And the worry is that this new human coronavirus EMC, which is also from bats, is essentially the very early stages of what we saw for SARS. So this is one of those, this is what we saw where we have very early infections from animals to people. And if the virus accrues these mutations along the way that allows for very high transmissibility, then it becomes a much more problematic public health concern. In my lab, we work on kind of two angles for SARS. So on one angle, we look at the actual virus itself and look at viral proteins that are important for disease. And what we've identified is several proteins that block the innate immune response. We've identified several proteins in SARS that inhibit those innate immune pathways. So that initial, very early response to the virus is inhibited in SARS-infected cells. And we've been figuring out what proteins are doing that and how they're doing it. The virus actually induces a very uncontrolled immune response. So instead of having a very steady process-like response to the virus, we get a very uncontrolled immune response where the actual host response to the virus is the thing that damages the lungs and causes death. What we've been able to show is that these proteins from the virus actually become very good drug targets. So several of the proteins, one of the proteins that we're working on is a protease that's important in the virus, and we're using that as in drug screens to identify drugs that when you treat cells or mice with or infected with the virus, we can then treat with the drug as a therapeutic to inhibit the virus. We have a project where we're looking in Maryland, right in our backyard, for viruses that are in bats to see if any of those have the capability of jumping from bats to people. We're working on that project previously, and now it's taking up speed to becoming much more important that there are these other viruses out in the environment that people didn't even know existed before and have been there for much longer than we knew about, that all have the capability of jumping.